started in just a second. Okay, so we'll get started. And again, what we're going to talk about here is what was originally scheduled to also be done during lab time. We're going to talk about redox reactions and specifically how to balance certain types of redox reactions in both acidic and basic solution, which is really the focus, I think, pretty much the entire focus of study assignment F, I believe is, and a little bit of some of the post lab questions and stuff like that, I think, on experiment 9. So again, this will help you out with experiment 9 and study assignment F as well. So as we talk about today during lecture here, and obviously if you do have questions, feel free to ask. Basically, redox reactions are oxidation and reduction reactions. And usually for us in sort of general chemistry, when we talk about oxidation, as we talked about before, that again is when we have a loss of electrons, and reduction is when we have our gaining of electrons. And again, a lot of cases you could follow the oxidation numbers like we did it in the lab, our lecture earlier today, to figure out what is happening. And again, sometimes just that basic number line sort of way of doing it. If somebody gets more positive, again, they're going through oxidation. If something gets more negative, they're gaining electrons and going through reduction. So as we talked about, which is effect in the other reactant. So it causes the reduction, the oxidizing in one of the reactants, which is our oxidizing agent, while the reducing agent causes the reduction in the other one. So usually when we talk about sort of loss of electrons, it's oxidation, and reduction are gaining of electrons. And again, people can remember it with the line across oxidation. You get reactants to product. Another definition and use agent from reactant definition of because in organic chemistry, oftentimes we'll deal with non-metal interaction. So it's oftentimes easier to follow either hydrogen being gained or oxygen being gained or lost, rather than sort of oxidation numbers and electrons. But in general chemistry, we usually will sort of focus in on these oxidation states, electrons being lost or gained. Now, when we go to balance just a basic redox reaction, like we talked about earlier, so for example, you always want to make sure that you have a balance and a balance zero as zero going through the and we can write our two half reactions for this, and our two half reactions, just like we saw before, should be balanced. So we have our two magnesiums, which is going through oxidation, going to go to 2 or Mng2 plus, and also our 2 electrons each, which means that we will actually end up with 4 electrons. So get that right. It'll be 4 electrons. Our 4 electrons. And that again would be our oxidation half reaction. We can recognize that by the electrons on the product side. And that's our oxidation half reaction. While our reduction half reaction will again be our electrons being gained. And again, because our electrons are on the reactant side, that is going to be our reduction half reaction. And again, when we add them back together, you want to always make sure, as we talked about earlier, that these electrons do cancel. In this case, they do. But if you do come across a situation where they're different, make that. Now, if you had a simple sort of half reactions where, you know, they didn't necessarily balance out. So for example, let's just say you had M and M3 plus 3 electrons, and you had 2 electrons plus N gives you N with a minus 2 charge. So if you were going to sort of add these guys back together, you cannot do it because, again, on this side, which would be our reduction half reaction, and on this guy, which would be our oxidation half reaction, we have different numbers of electrons. So before you would add them together, you would multiply the entire guy by 2 on the top, 3 on the bottom, again, because the common number there is 6 to get us to the same number of electrons. And will completely cancel out. So in a situation where you have two half reactions that do not contain the same number of electrons, before you would add them together, you want to make sure that you do have the same number of electrons in each. And again, that may require you to multiply one half reaction by a number, or even both half reactions by a number. Again, any questions on sort of what we were talking about earlier? Now, when we deal with a little bit more complicated sort of aspect of balancing these redox reactions, we sometimes are asked to balance these redox reactions in acidic or basic solutions. So acidic or basic solutions. And this is a little bit more complicated in terms of how you go about balance these guys. So let's talk about what we do for acidic first. For acidic, the first thing that you want to do is split up the reaction into its half reactions. So that means you should have an oxidation half reaction and a reduction half reaction. So that's the very first thing that you want to do is you usually be given the entire sort of equation. You want to split them up into their half reactions. The next thing that you want to do is balance all the elements. What means is, for example, if you have, say, 2 carbons on the left-hand side of a half reaction and 1 carbon on the right-hand side in that half reaction, just like you would balance an equation, you would put a 2 in front of the guy on the right with a coefficient, the big number, to balance it. Once you've balanced everything besides hydrogen and oxygen, we balance the oxygen by adding water. So we use water basically the oxygen. Something such as we have reaction, whatever maybe. And with this, on the left, on the other side, the right hand side, so every side will be balanced when. So for every water that you add to side, half reaction, the oxygen, then need actually, and that's not the so then obviously that you add. So if you added 2 waters to one side, you need 3 waters to the other side, you need 8 waters to the other side. Fuel, hydrogen balance. So what does that mean? It does not necessarily need to be a charge. It can be that. It also means you have a minus. So when you add electron, only two sides of the reaction can cancel out. So basically what that means is, like here, the electron in this one is on the left side, the electron in this guy is on the right side, and that's because ultimately they need to cancel out. So if you find yourself when you get to the half reactions of adding the electrons to the same side of the arrow, you're definitely doing something wrong because they will not cancel out. So they do need to cancel out. Once you've added the electrons, you're now ready to actually add both half reactions together. Like may require you to half reaction by a common number, may require you to multiply both half reactions by a common number or 2 different numbers to get it to there. Once you do that, you're going to, and if you do that correctly, at that point, you should have a balanced redox reaction or equation. It should be balanced at that point. And when we talk about it being balanced, it actually has to be balanced 2 ways. It has to be balanced like a normal equation, same number of elements on each side. And secondly, it needs to be balanced with the same charge, same overall charge on each side. So much like what we had on the bottom right, or bottom left there, left-hand side adds up to like -1. The right-hand side needs to add up to -1. Left-hand side +2, right-hand side +2. It needs to be balanced. This would be to give you the balanced equation in an acidic condition. Any question on those steps? We're going to do some examples in just a second to see how it all really works. Now, if you do have it in a basic solution, you look at your equation. I'm just going to make up one here. You will have a plus there, a plus b. So again, equation, just everything's balanced. What you do if it is basic is you look at your equation and you see how many H pluses you have. In this example here, I have 4 H plus. You would have 4 pluses to both sides. The side minus and H. We then cancel completely, and the other side will give us and it's still have and you just on each side. So basic conditions, there's multiple ways you could do it, but this is sort of the easiest way just to balance it in terms of the solution and then kind of fix it at the end by adding hydroxide to both sides. So these are the fundamental steps that you should follow when you're trying to balance a little bit more complicated redox reaction in acidic or basic conditions. So let's actually look at one here, kind of go through it together to show you how you actually do it. All right, so let's say we had this reaction here, and we want to balance it in acidic conditions. So we want to balance this guy in acidic conditions. Yeah, go back here for you. There you go. There you go. Good. Now, while you look at that, I'm just going to tell you before we're done here today, when we talk about sort of the study assignment, it's kind of written a little bit weird. I'm going to explain to you sort of a couple of things that you'll see in there that you can sort of ignore or sort of do the problem a certain way. So you all good on that? Okay, so let's take a look at one. No problem. And let's go through this here. Okay, so we're going to balance this guy in acidic conditions first. And the first thing we want to do is really break it apart into its half reactions. So you can really just basically take the two things that are related to each other. So obviously the irons are related to each other. So that would be one half reaction, which would be iron with a +2 going to iron with a +3 charge. Obviously, these both have chromium in it, so they're related to each other. And that would be our other half reaction here. Cr2O7 minus going to our Cr3 plus. Now, you also want to perhaps figure out, sort of what's going on in terms of what is being oxidized and what is being reduced. And if we look at the iron here, the iron is +2. This iron on this side is +3. So again, if you use that sort of number line, the iron is starting at +2, which is like here, and it's going to +3, which is going in this direction, and again in that direction. That means that the iron is going through oxidation. You could also do the same thing for the chromium, and we actually did that one, I think, in lecture in terms of its oxidation state. And if you go through the process of its oxidation state, oxygen is -2. That gives you -14 plus -12 with the -2 that's there. So this is going to give us +6 for our chromium here. Chromium is going to be +3 in this case. So again, if you look at chromium, he's starting out over here at +6 and heading in this direction towards +3. And in that direction, again, is reduction. So our reduction half reaction is here. This is our oxygen. And by means, again, would be our this oxygen. Any questions on how to figure that stuff out right there? All right. So the next thing that you want to do is balance everything other than oxygen, just like you normally would with a coefficient. So in this case, we have one iron and one iron here. So they're both balanced. We have one of each. Over here, we have two chromiums, but only one chromium on this side. So to fix that, we are going to put a 2 in front of the chromium. Again, we're just going to balance it like a normal reaction. So that takes care of all the other elements besides the oxygen and hydrogen. At this point, we now want to balance the oxygen. In the top half reaction, there is no oxygen, so we don't have to worry about it. In the bottom half reaction, I'm just going to rewrite it over here. In this reaction, or half reaction, we have 7 waters, which means we have 7 oxygens. And that means we need to add 7 waters to the right-hand side. So I apologize. We have 7 oxygen on the left. To balance out the oxygens, we're going to add 7 waters to the right. As we talked about, when we add the 7 waters, that is going to give us 14 hydrogens. So to make sure that our hydrogens are balanced, we would then need to go to the other side and add 14 H pluses. So that is how we balance the oxygen. Water to one side that needs the oxygen, H pluses to the other side to balance out the extra hydrogens that we got from the water. So what I'm going to do now is I'm just going to recopy the other half reaction underneath it at this point. So at this point, we balanced everything other than hydrogen and oxygen. We just balanced the oxygen and the hydrogen there with the water. The next thing we're going to do is now balance the overall charge on each side. Now, the easiest way to do this so you don't screw up is to actually do the overall charge on the each side. We want to make sure that we add electrons. So to balance out the charge, what we're going to do is add electrons. So we basically need to add electrons to whichever side needs the negative. So let's take a look here first at the iron. Overall charge on this entire left-hand side is +2. Overall charge on the right-hand side is +3. So in this case, we do need to add an electron to the right-hand side, and that will give us an overall charge of +3, and -1 is +2, and +2 on the left. Again, the charge does not have to equal 0. It just needs to be the exact same number on the left and right-hand side, the exact same charge, basically positive or negative number on right and left. If we add up what we got going here on the top one, we have 2 times 3 plus is +6 on the left-hand side. Water is neutral, so it has no charge. On the right-hand side, we have +14 from the hydrogens. We also have a -2. That whole thing is -2. That gives us, for the left-hand side, +12. So we have the right and from the left, on the right, 6 electrons to balance that out. -6 and +12 gives us a +6. Any questions up to that point there? Now, again, I'm just going to rewrite this so it's a little bit neater so we can see what's going on. So we have 6 electrons plus 14 H gives us and point where we now want to add both our oxidation and reduction half reaction back together. But before we could do that, the important thing is a couple of things. They're on opposite sides of the arrow, which is important. Again, if you're at this point and you from the side, we have together. We have the exact same number of electrons and so what we want to do then is, now that we have the same number of electrons, excuse me, in each half reaction, we're ready to add those back together. So what I'm going to do is, since I'm running out of room here, I'm just going to flip the page if you're good. And I'm just going to rewrite them on the next page. So what we got going on, again, was our top one, which we didn't multiply by, which was 6 electrons plus 14, and I gave a 3 and our 7 waters. Line bottom one, goes to the electrons. Again here, that is not needed. So since we have the same number of electrons, it's at this point that we can add both of these equations together. Everybody on the left-hand side of the arrow will see on the right-hand side arrow will see on the right. So just write down and everything on the right arrow. That moves something out of my way here. There we go. And we got 7 waters. We got 6 of the irons and 6 electrons. At this point, you could treat really the arrow as like an equal sign in math. So we can subtract basically these 6 electrons to the other side, and they will cancel out. At that point, I think that's everything that will cancel out. So we again will be left with 14 H pluses plus Cr2O7 2 minus plus 6 of the iron 2. We'll go to the other side where we would have Cr3 plus our 7 waters plus R6 irons with a +3 charge. Now, if I did not screw up or anything, it's a 50-50 shot at that, I think. This should be our balanced equation. And making sure again it's correctly the way it's left. That's two zeros, two right. 7 options on last side. One is 7 on last right. Also balance overall charge. And I'm going to go with +6 at that. And minus here, the +4. On the side, +6 is 18. +18 and +6 is +24. So we have +4 on the left-hand side of the arrow, +24 overall charge on the right-hand side of the arrow. It's balanced. We have the exact same number of elements on each side. It would also be balanced. And again, this would be your answer in acidic solution. Now, if we were going to do basic solution for this one, we would do every single step just like we did. We would come all the way down to where we ended up with, which is this equation here. And if we were going to do this in basic conditions, again, you would do everything acidic wise. And at this point, you would look at that final acidic equation and you would look for the H plus, which in this case is right here. And since we have 14 H pluses, we would add 14 OH minuses, not to just one side, but we would actually add it to both sides. And again, the side where we have H plus O7 minus plus R6 irons with the plus R2 charge, as you can see in the right side, it does not completely cancel out in this case, but it will reduce. So we will get a other side, and this will leave CR2 plus 6 irons. You see 2 CR plus 6 and it should still be balanced the same two ways with the same number of elements. So less 14 is plus 10 is only. You usually don't have to necessarily obviously do both. Maybe as you do basic, you do, but obviously if you were doing acidic, we'll come back. You would just do the top part. Any questions on that one there? All right, so let's take a look maybe at another one. And I'll tell you what, why don't you do this one here? And let's do it in basic conditions. So why don't you take maybe 5 minutes or so and give that a go. And if you can, write down this equation right now, because I'm going to go look for something for the lab so I could kind of show you when you look at it in lab. So take a second here, write down that equation, and then balance it in basic conditions. Take about 5 or so minutes or so to do it, and then we'll go through it, make sure everybody's on the same page. And while you're doing that, again, I may be quiet. I'm just going to go look for the lab so I could sort of demonstrate what you need to kind of do for that part. Okay, so then let's take a look and kind of see what's going on with this one. And hopefully that will come soon. All right, so when we look at this, what we want to do again is just follow the steps. So the first thing that we want to do is basically break this apart into its half reactions. And hang on one sec, I just got to fix something. See if that works here, maybe. Sorry about that. Hang on one sec here. All right. Try a third time here at charm, maybe. All right, so the first thing that we want to do is, again, break this apart into its half reactions. So really you could start with just the two things that are related. So in this case, I minus is related to I2. So those two things are definitely related to each other. The other half reaction, MnO4 minus, is related to MnO2. Again, we could look at our oxidation sort of number and see what is going on in terms of what is being oxidized, what is being reduced. Over here, our I minus is -1. Our I over 2 over here is 0. So again, in terms of the I, we are going from -1 to 0, which is going to and that make this and to our M and over here, that's my the case is plus the end plus over more for that and the options this region. Agent. Any questions on that? If I can see the chat box kind of disappeared on me here. There it is. Okay. All right. So once we have it broken apart into its half reactions, the next thing that we want to do is balance everything other than oxygen and hydrogen. So in the case of the top one, I minus that goes to I2. We have 2 iodines on the right, but only 1 on the left. So we're just going to balance it like a normal reaction and put the 2 in front. There is no oxygen in this one, so we don't have to worry about it. Our MnO4 minus going to our MnO2. We have 1 Mn on both sides, so we don't have to worry about it. So the next thing that we want to do is balance the oxygen. So on the left-hand side on the bottom, we have 4 oxygens. Right-hand side, we have 2. So the right-hand side needs oxygen, and it needs 2 of them. So we're going to add 2 waters to the right. Remember that for every water that we add to one side, we have to add 2 H pluses to the other, and that will give us 4 H pluses to the right-hand side, or left-hand side. Again, if you don't do that, then you will be unbalanced in terms of the hydrogen. So for every water that you add, 2 H pluses need to go to the other side. Any questions up to that point? Let's see here. All right, so okay. All right, now I got it back. Thank you. All right, perfect. I know. I just had to get that chat box. It just kind of disappeared on me. Got it back now, so you should be good. Okay, so at this point we have balanced everything besides oxygen and hydrogen. We have balanced oxygen by adding water to one side and H plus to the other side. The next thing that we want to do is balance out the charge on each side of the half reactions. Again, we're going to use electrons to do so. So looking at the top half reaction, overall charge on the left-hand side is 2 times -1, which is -2. Overall charge on the right-hand side is 0. So the side that needs the electrons is the right-hand side. And to get us to -2, we would need to add 2 electrons. Again, we're adding negative charge, so we would need to add it to the right-hand side. This also makes sense based on what we saw earlier, that this is the oxidation half reaction, which means when we add electrons, they should be added to the right-hand side. So that's always where we add the electrons in our oxidation. We want to do the exact same thing to the bottom half reaction. We want to balance out the charge by adding electrons. Overall charge on the left-hand side, we have 4 plus 4, and -1 gives us a +3 overall. Right-hand side, this is neutral, has no charge. Overall side here is 0. So the side needs electrons on the left side. And we have 0 on the left hand and overall charge is on the right hand. So again, we're going to all the overall charge on the side and the electrons on the correct side again. It's actually as a reaction reaction. Any question? Now we're at the point we want to add both of the half reactions together, but again, because we have electrons in that reaction and we have electrons in this reaction, they're not the same number. They always has to be the same number before you add them together. In this particular case, the top one has 2 electrons, the bottom reaction has 3. The common number between 2 and 3 is 6. So to the reaction, we will have something by 3, multiplying by 2 to get us to 6 electrons. So the goal here is to get the same number of electrons in each half reaction. And when we do that, I'm just going to rewrite both reactions underneath, multiplying the top one by 3, 6 minus 3 and distribute that to everybody that's there. We're going to do the same distribution everybody, and you have a 6 plus 2 and 4 minus 2 and 2 plus again. Now that we have the same electrons on the arrow, we could add these equations together. In case the electrons to cancel, the opposite side of the arrow. Again, everything on the left is on the left, everything on the right is on the right. This is going to give us 6 plus 8 plus 2 and 4 minus. On the side of the arrow, we have 3 2's plus 2 and 2 plus 4 bring down on the left-hand side of the arrow, and on the right-hand side of the arrow, again, just canceled out the electrons in this case. Again, if you do this correctly, the electrons should cancel out completely. If we were going to balance this equation in acidic conditions, that is technically what we got right here. This is the equation that's balanced in acidic conditions. Again, you have 6 I's on both sides, 8 hydrogens on both sides, 2 MNs on both sides, 8 oxygens, 8. Overall charge on the right and 0. Charge on the right is also 0 as well. But in this particular problem, we were not going to do it in acidic. We are going to do it in basic conditions. So really the difference between acidic and basic is not that much. You pretty much can do everything just like we did in acidic conditions. And now you can balance it for basic. So again, to balance it for basic, what I'm going to do is just rewrite the equation. 6I minus plus 8 plus 2 and plus 2 plus 1. When we do basic, we see H plus H plus not actually both sides. Now you have H minus H plus and 4 and at this point, what you usually have is we'll have water sides, so waters by subtracting 4 and then 4 water left. 6 plus 2 gives us 3 plus 2 and if we do this again, go back to make sure we have hydrogens on the right, 4 oxygen there, and 8 more is 12 oxygens on the left. 4 oxygens on the right plus 8 more give you 12. 6 iodines on both sides and 2 MNs on both sides. Overall charge on the left is -6 and -2. Right, is balanced both ways, both in terms of elements and also in terms of charge. Any questions on any of those steps there? Again, there's a lot of different ways you can kind of do this, but the easiest way is to balance everything just like they're acidic. And if it's basic, then you need to add, again, the OH minus to both sides. It's important there, not just one side, but both sides. Any questions on that there? Okay, so let's take a look at actually a couple from the study assignment just to kind of show you a couple things and how to deal with them and really what they mean. So let me find that there. All right, let me flip the page, I think. Oh, did not like that. Okay, so this is actually one right from the study assignment. I think it's number 2, as the number says there, it's 2A. And a couple of things that you will see in the study assignment, the way that the equations are written. And the first thing is they were really written, I think, for a purpose, but not that important for us. But you will see in this particular case that we see H plus and we see water. And in this study assignment, if you see H plus on one side and you see water on another, could be the other way around, water on the left and H plus on the right. Basically, what that is telling you is you should balance this equation in acidic conditions. And to do that, really, you could look at this equation like this, MnO4 minus plus SO3 2 minus goes to SO4 2 minus and Mn2 plus. You could literally take the H plus and H2O out of it to begin with. It is telling you that it's acidic, and that's why it's in there. Sometimes people want to use it while they're balancing it and kind of messes them up a little bit. And if we were going to do this, just to go through this again, we would break this apart into our half reactants, which is related to each other. And they're place. And you would want to figure out what's happening, what's being inside, what's being the oxygen here is minus. So again, this is our half reaction. By default, our oxygen reaction, that the oxygen 2 -6, and then -2 over, so that's plus through there, and this is -2, which is 8, and then this is going to be 6. We're actually starting at 4 and going to 6 over oxygen. So we follow basically 4. The next thing we want to do is balance. There's 4 oxygens on the left, on the right, so top guy right to balance. Also as again, because the water is 2H plus water that you add. On the right, actually only needs water, but we want to add 2H plus in this case. Now that we have balanced both the oxygen and the hydrogen, we want to balance the charge side by adding electrons. Overall left side is plus 1, plus overall charge is plus 2. That means 5 electrons get the plus 2 sides. We'll add 5 electrons. One side is minus 2. Charge on the right is plus 2, which is immediately added to the right side. We'll 2 electrons. And because on the right hand oxygen, electron will save that. At this point, you add them together, but you cannot these together. You have 5 on the first reaction, 5 on the second. So you multiply that the equation is 2. The equation we find of this is to get everybody to the same number of electrons. And if I rewrite those equations, the top equation will now balance. The other side, here we need to be all the way across that equation. We have 5 plus 3 side, and all we have 10 to the right hand side, to the left, that's going to leave H plus cancel. They cancel completely. They made if you on the left hand 0, there are 5. On the right hand, there's 1. which is going to leave you when you use this. And I think that's it. Plus and O are 5 over E minus goes to 2 and 2 on the right. Everything we should be balanced both in terms of element and charge. There are 6 hydrogens, 6 on the right, 10 on the right, 8 there, 5, but that's 23 more giving you 5 sides in terms of elements. Overall, hydrogen for the N4 and so 3 minutes. That also is a minus overall charge. On the right, we have Mn 2 and 5 on the left side. So this again would represent the balanced equation for acidic conditions, which is what we balance for here. Any questions on any of those steps? Now that we have the balanced equation, we can now go back to the original equation in the study assignment, and we will see why there was an H plus on the left and a water on the right. That is because when we finish balancing it, yeah, go ahead. What's your question? So the question is, why did we add 8 H pluses and 4 waters to the top equation? I'm assuming you're asking about. So let's just back that top equation up and look at it. So before we added the waters, what we had in that top equation, I'll rewrite it over here. What we had was MnO4 minus and Mn2 plus. So the purpose of adding the water is to balance the oxygen. And for every water that you add, in addition to the oxygen that you're adding basically 2 hydrogens. So that's why for every water, we actually have to add 2 H pluses to the opposite side to make sure that when we're all done, we're not going to be short any hydrogen, because by adding the water, we're kind of artificially adding hydrogen there. So we do have to add the H pluses to the other side. So when we looked at this, on the left-hand side, we had 4 oxygens. On the right-hand side, there was none. So that's why the first option. So in order not to be short, we need 8 hydrogens to balance it out. So for every water that you add to one side, you need to balance out the other side with the H plus. Otherwise, when we get to the very end, you're going to be short hydrogens. Also, if you happen to have started, so just for example, let's just say, I don't know, let's just say we had something like this. Totally different than this problem, obviously. So let's say we had a half reaction that started out like this. We actually have more inside. This is a place we had at the beginning. Those hydrogens again. Otherwise, you'll find yourself short hydrogens if you don't kind of do that. So another place where you might need to just add H plus is if you start out with a half reaction and you're kind of short hydrogens to begin with, you could add H plus to the other side to balance out those hydrogens. Other questions on any of those steps there? Okay, so going back to why we kind of ignored these 2 guys here at the very beginning, the H plus and the H2O. I personally didn't write it, but I think the purpose of why it's there is because when you correctly balance this equation like we did bottom, you will see that the H plus ends up on the left-hand side, and the water here ends up on the right-hand side. And I think it was originally put in there so that at the end you could go back and just put the numbers, like 6, 2, a 5 or whatever we had. Actually, the 6, and that was the 5. Just kind of throw the coefficients in there, the right ones, not the bad ones, the right ones. Just kind of put the numbers in, and that way somebody could grade it really easily by putting the numbers in. So this is a way you actually could check yourself. When you do it correctly, your H plus and H equation. So that's why you technically convert in all those equations that you see. And again, you can kind of use it to check yourself at the end that ended up balancing correctly in the H2O on the side as well. Another thing that you'll see when you look at that study assignment is how this one was H plus, which means acidic. You will also see one that looks like this. And when we look at this one, we see not H plus, but we see OH minus, and we see water. Deal to begin with. You should rearrange this with and begin acidic or acidic and reduction on that side. So I tell you, how about one last one? If you like, you could work on this one for 5 minutes or so, and then we will go over it, and you can at least see how you're doing. If that sounds good to you. So why don't you take 5 minutes or so, kind of start working through that. Yeah, I'm gonna post this so you can watch it again and all that good stuff. Yeah, so always, if it's basic, the easiest way to do it is just to go through all the steps like it's acidic. And then again, when you get to the end, after you have it technically balanced in acidic conditions, that's when you want to add that OH minus to both sides. Okay. And then combine to make water and then reduce it down. So I tell you what, guys, why don't you take about 5 minutes or so, kind of work your way through it, and then we'll go over it. And I'll be quiet for a second. If you have questions, go ahead. I know it's very tight in the manual. If you want to do it on separate sheets of paper, you can. It's kind of a lot of it looks like you could do it really quickly in a very small space, but you actually need a lot of room to work a lot of the ones out in that study assignment. All right, so take the 5 minutes or so, work through it, and then we'll go through it, see how you're doing, and then maybe we'll call it a night after that. Okay, so let's take a look and see how we're doing, how we're making some progress. So again, especially for the ones in the lab manual, they're all kind of written like this. So as we mentioned at the beginning here, you do want to kind of ignore the OH minus in this case and the H2O, just like we sort of ignored the H plus and H2O in the other one. Again, you could pretty much look at it when you look at those in the lab manual, anything that has H plus in it, you should balance it in acidic conditions and not hit the button. Anything with the OH minus, again, you should balance that in basic conditions. So ultimately, these are here for at the end when you're all done in that very small space that you got there and you balance these equations. These guys is pretty much the side they should end up on. So we kind of know up front that the OH minus should end up on the right, the water should end up on the left. And it's a good way, I guess, to kind of check yourself when you do these. In most problems that you would probably get, you would usually have the equation, and usually in parentheses it'll say acidic or it may say basic there, and that's usually how most people will sort of tell you to balance it, acidic or basic, by just sort of doing that. So same idea here. We want to first split these guys off into their half reactions, and then it's just basically the two things that are related to each other. So obviously Bi on both sides should be related to each other. And then the second guy has Mn on both sides, and those guys would be related to each other. Just like we've done before, we could figure out sort of the oxidation numbers here. So this is going to be 0 because, again, it's by itself. It's not combined with anything, so we'll have an oxidation number of 0. Our Bi with a +3 will be +3. So again, if you sort of did that number line move, we're starting at 0 and we're ending at +3, which is moving in this direction, which tells us that the Bi is going through oxidation. And by default, that means that this should be our reduction half reaction. Again, once you figure out one, you'll know what the other one is. But just to verify, we've done this guy a couple of times at this point. That's going to be +7 for the Mn. Our oxygen over here is -2, and there's no charge, which means the Mn in this case is +2. The Mn is starting over here at +7, heading in this direction to +2. So that would be reduction for our Mn. Any questions on that so far? So remember that once you have balanced, I basically split it off into its half reactions. The next thing you want to do is balance everything but oxygen and hydrogen. On the top half reaction, we have a Bi on both sides, so that's good. It's balanced. On the bottom one, we have an Mn on both sides, so that also is balanced, so it's good. So at this point, we then can move on to the oxygen. Top reaction, there's no oxygen on either side, so we don't have to worry about it. Bottom reaction, we have 4 oxygens here, only 1 oxygen here. So again, to balance the oxygens, we use water. And the side that actually needs the water and the oxygen is the right-hand side. We would need to add 3 waters. Again, that 3 water is going to give us the 3 oxygens that we need to balance it. But again, as we talked about, the consequence here is we then will need to go to the other side so we don't end up being short and add the 6 H pluses to the other side, strictly because we added 3 waters to the right, which gave us more hydrogen, so we need to add it to the left-hand side. Any questions up to that point? At this point, once you have added the waters and you've added the H pluses, this is the point where we're going to go and balance the charge on each side. And again, the easiest way I think to do that is just to look at the overall charge on each side. You could go element by element and figure out everybody's oxidation state. but there's really no need to do that for you because it's already done for you with the charges. So if we look at this side, we have 0 in terms of the overall charge. Right-hand side, we have +3. So 0 on this side, +3 overall on this side. That means that the right-hand side is going to need 3 oxygens to get this side to 0 now. And that also makes sense. Again, it's an oxidation, and our electrons are on the right-hand side, so that's all good. Now, when we look at the left-hand side, we have +6 for the hydrogens. We have -1 overall for this guy all together, and that's going to give us a +5 on the left-hand side. Right-hand side here is actually 0. 0 for this guy, 0 for the guy on the right. Overall charge is 0. To balance that out, that means that actually the left-hand side here will need 5 electrons. Also makes sense because this is a reduction. Electrons on the left-hand side, which means it's a reduction, going to get us now to 0 overall charge on the right-hand side. So again, what I was talking about, why you don't necessarily have to, why did we add the 5? Yeah, so we added the 5 electrons to the left-hand side. Let me just move something here to get a little bit of room. So on our reaction before we did anything, we had 6 H pluses, and this goes to MnO and 3 waters. So this guy here is going to contribute +6. Again, this entire thing, that polyatomic ion all together is only a -1 charge. And that all together gets us to +5. While on this side, this guy is 0, is neutral. This guy is 0, which gets us to 0. So again, to balance it out, that's why we needed the 5 electrons, which basically will get us to 0. Other questions on that? So now that we have the electrons added, we want to add back both of these equations. But again, we need to make sure that we have the same number of electrons in each half reaction. And of course, on this worksheet, you don't. So the common number is 15. We have 3 electrons in the top, which means we need to multiply the entire thing by 5. We have 5 electrons on the bottom, which means we need to multiply that entire bottom equation by 3. That's going to give us 15 electrons in each of those. And again, I'm just going to rewrite each of those equations below it and multiply each of those numbers in. So that's going to give me 5 of the BIs goes to 5 of the BI 3 pluses plus our 15 electrons. Multiplying the bottom equation, that will get us 15 electrons plus 3 times 6 is 18 H pluses plus 3 MnO4 minuses gives me 3 MnO and 9 waters. All right, at this point, we do have the same number of electrons on opposite sides. And we want to keep everything on the left-hand side of the arrow on the left, everything on the right-hand side on the right. You could bring down the electrons if you want, but they should cancel. So because they're on opposite sides and the same, they should completely cancel out, which should always be the case. So if you again get to this point and you add these together and they don't completely cancel out, you did something wrong for sure. Okay, so those electrons should always 100% cancel out. We're going to leave everybody on the left. So that's going to get us 18 H pluses plus 3 MnO4 minuses plus 5 Bi. And that should be everybody on the left. On the right-hand side, we have 5 Bi3 plus 3 MnO, and 9 waters. At this point, we essentially, which is not what they're asking for in this question, this is essentially the balanced equation in acidic conditions. You could verify that by taking a look, and if we look, what we will see is we have 18 hydrogens on the left, 18 on the right, 3 of the MNs on the left, 3 on the right. We have 12 oxygens on the left. We have 3 oxygens on the right, and 9 more make 12. 5 BIs on the left, 5 BIs on the right. Overall charge, if we look at it, is 18 positives on the left plus 3 negatives, gives us a plus 15 on the left, and on the right hand side plus 15. So again, if you were asked to balance it in acidic conditions, you would put a box around it and be done. But again, because of here we're looking for our basic conditions, we have to do that last couple of steps where now that we have it balanced in acidic conditions, we need to look at that equation and find our H pluses, which in this case is 18, and we will add 18 OH minuses, not just to one side, but to both sides. So 18 OH minuses to this side. Again, at this point, these H pluses and OH minuses will come together to give you 18 waters. Everything else will remain the same. And usually in this case, the last thing that you need to do is look on both sides. And as you will typically see, we got 9 waters on the right. We got 18 waters on the left. That also will reduce down. Again, it's like subtracting 9 waters to both sides. When you do that, that's going to leave you 9 waters on the left-hand side, plus our 3MnO4 minus, plus our 5Bi, gives you 5Bi3 plus, 3MnO, and 18 OH minuses. And again, if everything went right, which we hope it did, you could always edit it out later, I suppose. This is it balanced in basic conditions. Just to verify, we have 18 hydrogens on the left, 18 hydrogens on the right, 9 oxygens here, plus 12 more here. That's a lot. That's, what did I say there? 9 and 12. A lot of math. That is 21 oxygens, I hope. That's 18 oxygens here, and 3 more give you 21. We have 3 MNs on both sides, 5 BIs on both sides. So again, we're balanced in terms of a normal equation, same number of elements on each side. Overall charge, when we kind of look at the overall charge on the left, that's 0 for the water. That's -3 for the MnO4. That's 0 for the BI. That gives you a grand total of -3. On the right-hand side, that is +15 for the BI3 plus. That's 0 for the MnO, and that's -18 for the OH minuses. That gives you a -3 on that side. And again, that means it's balanced both in terms of elements on both sides, which it should be, and also charge on both sides. And because of this worksheet or study assignment, you could check yourself. And we do see in our balanced equation, the water's on the left and the OH minus is on the right-hand side. Again, it's a way you could kind of check yourself. And like I said before, I think when he wrote it, he just assumed people would come back and just kind of fill in the numbers when they're done working on it. Although it gives you sort of that impression that you could do it really quick, like a normal equation. But you do have obviously a lot more sort of steps that she has to do this. Any questions on how to balance these equations? I hope it's starting to make sense at least. So definitely in the study assignment, you'll see all those kind of things. So just ignore the H plus H2O or the OH minus or the H2O, kind of like what we did here in these examples, and you should be fine. Good, I'm glad. Any other questions? You need a lot of paper. I need a lot of screen. I'm almost out of screen here. Any other questions I could help answer for you on this stuff? So after watching this, and if you're watching this, the recording as well, you should be able to now hopefully complete study assignment F. It's a lot of this balancing, so it is going to take some time to do. And you should be able to, I think, complete the experiment as well, experiment 9. So again, both of those things are up there along with study assignment E, which is our net ionic equations, the stuff that we did previously, I think last week. So you should be able to start working through all these experiments. And again, I think study assignment E is due this week, which I guess if you're listening to the recording, this week is April 21st, I think, right now. So it's due at the end of this week, and study assignment F and experiment 9 is due at the end of the following week, which I think is like the 29th or 30th of April, somewhere in that ballpark. Any other questions I could help anybody with? Okay, then I probably am going to stop unless you do have questions. If you do have other questions, feel free to email me or ask, and I will see you on Thursday. Thank you for coming. Have a good night. Okay, good. Have a nice night.